Welcome to a journey into the deepest mysteries of our universe, where we'll explore 100 remarkable facts about black holes, those cosmic phenomena that represent perhaps the most extreme expression of gravity's power in the cosmos. This is not a sensational tour through space designed to frighten or excite, but rather an invitation to contemplate, to wonder, and to drift gently into understanding as we explore these magnificent mysteries together. Black holes have captivated the human imagination for centuries, yet only in recent decades have we begun to truly understand them through a combination of theoretical physics and observational astronomy. They challenge our intuitions about reality itself, forcing us to ask profound questions about time, space, matter, and the very nature of existence. Before we venture into this exploration, I want you to understand something essential. Black holes are not hypothetical constructs or science fiction fantasies, but rather observable, measurable phenomena that exist throughout our universe, and their discovery represents one of humanity's greatest achievements in understanding the cosmos. Let me begin with our first fact. Black holes form when massive stars reach the end of their lives, and this process is called gravitational collapse. When a star much more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity, and it catastrophically collapses inward, compressing all its matter into an incredibly small volume. The second fact reveals that this collapse creates something unprecedented, a region of space-time so warped by gravity that nothing, not even light itself, can escape from within its boundaries. This boundary is called the event horizon, and it is perhaps the most important concept in understanding black holes, for it defines the point of no return, the cosmic threshold beyond which existence as we know it becomes fundamentally altered. The third fact tells us that the very center of a black hole is called the singularity, and according to our current mathematical models, all the matter in the black hole is compressed into an infinitely dense point at this center. However, and this is crucial to understanding modern physics, many physicists believe that quantum effects we don't yet fully understand will prevent true infinities from occurring in nature, suggesting that the singularity might be something quite different from what our classical equations predict. The fourth fact is that black holes come in different sizes, and these sizes matter tremendously for understanding their behavior and their role in the cosmos. There are stellar black holes, formed from the collapse of individual massive stars, containing perhaps 10 to 20 times the mass of our Sun, and their event horizons might span only a few kilometers across. Then there are supermassive black holes, those cosmic titans lurking at the centers of galaxies, containing millions or even billions of times the mass of our Sun, with event horizons that could swallow our entire solar system. And these behemoths shape the evolution of entire galaxies through their influence. Between these extremes lie intermediate black holes, those mysterious objects whose existence has puzzled astronomers, and their scarcity, if indeed they are scarce, presents one of the enduring puzzles in contemporary astrophysics. The fifth fact presents something genuinely astonishing. The smallest theoretically possible black holes could be as small as a subatomic particle, yet contain the mass of a mountain, creating a density so extreme that a teaspoon of such material would weigh as much as all the mountains on Earth combined. These primordial black holes might have formed in the chaotic first moments after the Big Bang, and astronomers continue searching for evidence of these tiny cosmic remnants. The sixth fact explains that when matter spirals toward a black hole, it doesn't simply vanish into darkness, but rather heats up to extraordinary temperatures, reaching millions of degrees and radiating enormous amounts of energy in the form of X-rays, ultraviolet light, and radio waves. This radiation is so intense and so bright that black holes surrounded by infalling matter become some of the brightest objects in the entire observable universe, paradoxically making the invisible gravitational demon visible through the radiation of material falling toward it. The seventh fact tells us about the first black hole ever discovered, Cygnus X1, identified in 1971 through X-ray observations, marking a transformative moment when astronomy transitioned from theoretical speculation to observational certainty. This discovery showed the world that black holes were not merely mathematical artifacts, but real objects orbiting in space, circling companion stars and devouring material from them in a cosmic dance of gravity and radiation. The eighth fact reveals something profound about gravity near a black hole. Einstein's theory of general relativity predicted black holes would exist long before we had observational evidence, and this remarkable achievement demonstrated the extraordinary power of mathematical physics to reveal hidden truths about our cosmos. Einstein showed that massive objects warp space-time itself, curving it like a ball placed on a rubber sheet. And at the extreme end of this warping lies the black hole, where space-time curves so dramatically that it closes off from the rest of the universe. The ninth fact is that the Schwarzschild radius is the mathematical term for the size of a black hole's event horizon, calculated by a brilliant physicist named Carl Schwarzschild in 1916, just months after Einstein published his theory of general relativity. This radius depends directly on the black hole's mass. A black hole 10 times more massive than another would have an event horizon 10 times larger, following a simple but profound mathematical relationship that governs all non-rotating black holes. The 10th fact creates our first major curiosity gap, and I want you to sit with this question. If black holes are so dark and invisible, how could we ever detect them, and how do we know they're really there? This question drives much of modern black hole astronomy, and the answer reveals the ingenuity of human observation and the power of gravity itself to reveal what would otherwise remain hidden forever, drawing us deeper into this cosmic mystery. Now imagine yourself standing at the edge of an event horizon and contemplate what would happen to your body and your perception of time itself. For this thought experiment reveals something truly extraordinary about black holes and the nature of reality. If you were to fall toward a supermassive black hole, say Sagittarius A star, at the center of our galaxy, the gravitational pull would not be equally intense across your entire body at first. The 11th fact explains that this unequal pull is called tidal stretching or spaghettification, and depending on the black hole's size, you might actually cross the event horizon feeling relatively normal, experiencing no sudden catastrophe at the boundary, though eventually the gravitational differences between your head and your feet would become so extreme that you would be stretched like spaghetti. But here's where it becomes truly mind-bending. The 12th fact reveals that time itself behaves strangely near a black hole in ways that would seem like science fiction if they weren't grounded in Einstein's proven theory. An observer watching you fall toward a black hole from a safe distance would see you slow down as you approached the event horizon, and in their reference frame they would see you freeze at the boundary, your image becoming more and more red-shifted as gravity slowed the light escaping from you. Yet simultaneously in your own reference frame, you would experience time as normal and would cross the event horizon without noticing anything special at the moment of crossing. Though beyond it, you would face increasing gravitational forces until eventually they became overwhelming. This strange duality of time perception, where time passes normally for the falling observer but appears frozen to a distant observer, reveals something profound about the nature of time itself. It is not universal, but relative, not absolute, but dependent on gravitational fields and velocity. And black holes represent the extreme where this relativity becomes visceral and inescapable. The 13th fact tells us that this phenomenon was not merely theoretical speculation, but has been indirectly confirmed through multiple lines of observational evidence accumulated over decades of careful astronomical work. The 14th fact introduces us to active galactic nuclei, which are the incredibly luminous centers of distant galaxies, powered by material falling into supermassive black holes. And some of these objects, called quasars, can shine with the brightness of trillions of stars, combined outshining entire galaxies of billions of stars each. When astronomers observe these quasars, billions of light years away, they are seeing the universe as it was billions of years ago, and they notice something remarkable. Quasars were far more common in the early universe than they are today, suggesting that black holes were more active and more numerous in the young cosmos. This realization leads to the 15th fact, which is that galaxies and black holes have evolved together throughout cosmic history, and the growth of supermassive black holes appears intimately linked to the growth of the galaxies around them. The 16th fact reveals something that contradicts a common misconception. Black holes are not cosmic vacuum cleaners, constantly devouring everything in sight, but rather quite selective and stable objects around which material can orbit safely if it maintains a proper distance. A planet could theoretically orbit a black hole just as safely as it orbits a star, maintaining stable orbits at distances beyond the tidal disruption radius where gravity becomes lethal. The 17th fact is that Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy, contains approximately 4.1 million times the mass of our Sun, and it sits only about 26,000 light-years from Earth, relatively nearby on cosmic scales. Around this black hole orbit dozens of stars moving at incredible speeds, circling this invisible cosmic monster in orbital dances that take years to complete. And by measuring how these stars orbit the black hole, astronomers have calculated its mass with remarkable precision. The 18th fact tells us about a monumental achievement in observational astronomy. In 2019, the Event Horizon Telescope, an international collaboration combining data from radio telescopes around the entire world, produced the first direct image of a black hole. This black hole resides at the center of the galaxy M87, about 55 million light-years away, and the image showed a glowing orange ring of light circling a dark shadow, representing the first time humanity ever saw the silhouette of a black hole against the background radiation of matter spiraling around it. The 19th fact is that this image had profound psychological and philosophical significance for humanity, for seeing is believing, and this image confirmed with unprecedented vividness that black holes were not merely theoretical constructs, but real observable phenomena existing in the cosmos. The 20th fact reveals something even more remarkable. In 2022, the Event Horizon Telescope captured a second image, this time of Sagittarius A star, the black hole at our own galaxy's center, providing even more evidence for the reality of these cosmic objects and allowing astronomers to test Einstein's theory of relativity in the most extreme gravitational environment humans have yet observed. These images represent more than just scientific achievement. They represent a moment when humanity collectively witnessed something that seemed impossible just decades ago. We saw a black hole, and that image will forever change how we understand our place in the cosmos and our relationship to these magnificent mysteries. The 21st fact brings us to one of the deepest mysteries in theoretical physics, the information paradox, a puzzle that has captivated the world's greatest minds and challenged our understanding of how the universe works. When matter falls into a black hole and crosses the event horizon, it appears to be lost forever, erased from the observable universe, and this raises a profound question. Does information get destroyed in the universe, or is it somehow preserved? In classical physics, information is never destroyed, but merely transformed, yet black holes seem to violate this principle. And this violation disturbed physicists deeply because it suggested that the universe itself might operate in ways fundamentally contradicting what we thought we knew. The 22nd fact is that in 1974, Stephen Hawking proposed a revolutionary solution. Black holes are not completely black, but rather emit radiation due to quantum effects near the event horizon. This Hawking radiation emerges from vacuum fluctuations at the boundary of the black hole, where quantum mechanics allows particle-antiparticle pairs to briefly exist, and sometimes one particle falls into the black hole while the other escapes, causing the black hole to lose mass and eventually evaporate entirely. This discovery suggested that information might somehow be preserved in subtle correlations in the radiation the black hole emits, though the precise mechanism remained mysterious for decades and continues to inspire theoretical research today. The 23rd fact reveals that smaller black holes would evaporate much faster than larger ones due to Hawking radiation, and a primordial black hole formed in the early universe might have already exploded in a burst of gamma rays. A black hole with the mass of Earth would take an incomprehensibly long time to evaporate, approximately 10 to the 50th power years, far longer than the current age of the universe. Yet eventually, even the largest black holes would fade away into nothing but radiation, suggesting that nothing in the universe is truly eternal. The 24th fact tells us something profound about human nature and scientific inquiry. This information paradox has remained unsolved for 50 years, and the greatest physicists of our time continue working on it, illustrating how deep mysteries can persist even in our highly advanced civilization. This unresolved puzzle reminds us that despite our tremendous progress, the universe still holds secrets. And perhaps this is as it should be, for without mystery, without the unknown, the human spirit loses its drive to explore and understand. The 25th fact shifts our focus to gravitational waves, which are ripples in spacetime itself, caused by the acceleration of massive objects, and black holes produce some of the most dramatic gravitational waves in the cosmos. When two black holes spiral toward each other and merge, they release gravitational waves of such tremendous power that the energy released equals the total mass energy of millions of suns, all released in the form of vibrations in space-time itself. The 26th fact is that these gravitational waves travel at the speed of light through the cosmos, carrying information about distant collisions to Earth. And in 2015, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves from merging black holes for the first time in human history. This detection was so profound and so important that it earned a Nobel Prize and opened an entirely new window through which to observe the universe, proving that gravity itself can be used as a medium for communication across the cosmos. The 27th fact reveals that astronomers can now detect black hole mergers happening billions of light years away by measuring minute disturbances in spacetime, vibrations so subtle that they cause the arms of the gravitational wave detector to move by only a fraction of the width of a proton. Yet our instruments are sensitive enough to detect this cosmic whisper. The 28th fact tells us something deeply moving about our relationship to these phenomena. Black holes inspire wonder, precisely because they represent the limits of our understanding, and perhaps our drive to comprehend them reflects something fundamental about human nature itself, our hunger to push understanding into new territories. The 29th fact is that black holes appear not just in scientific literature, but throughout human culture, in our stories, our myths, our science fiction, and our art, suggesting that they've captured the human imagination in ways that transcend mere scientific interest. The 30th fact creates a profound realization. When we study black holes, we are not merely studying exotic astronomical objects, but rather probing the deepest nature of reality itself, and every fact we learn about them adds another piece to the puzzle of existence. As we conclude this extended meditation on black holes, consider the unity that emerges from all these facts. From the formation of stellar black holes to the discovery of supermassive galactic engines, from the theoretical prediction by Einstein to the direct observation by the Event Horizon Telescope, from the information paradox to the detection of gravitational waves, these fragments of knowledge weave together into a tapestry, showing us that the universe is far more magnificent, far more mysterious, and far more beautiful than our everyday experience suggests. Black holes represent the frontier, where theoretical physics meets observational astronomy, where mathematics encounters reality, and where the universe reveals its deepest secrets to those patient and clever enough to listen. They remind us that despite all we have learned and all we have achieved, mystery persists, wonder remains, and the cosmos continues to invite us into deeper understanding. In the contemplation of black holes, we contemplate ourselves and our place in the universe. And we recognize that we are part of a cosmos so intricate and so profound that even our greatest minds can only begin to comprehend its true nature. May this journey through the darkness leave you with a sense of peace, with deepening appreciation for the magnificent mysteries that surround us, and with the understanding that you share this universe with phenomena so strange and so beautiful that they seem almost impossible until you encounter them through the lens of science. The universe whispers its secrets to those willing to listen, and black holes are among its most profound utterances, speaking to us across the void about the power of gravity, the nature of time, the limits of knowledge, and the boundless potential of human curiosity to illuminate even the darkest corners of existence. Now let us venture deeper into territory where the laws of physics themselves seem to transform, and where space-time behaves in ways that challenge our most fundamental intuitions about reality and existence. The 31st fact reveals that not all black holes are created equal, for some spin while others do not. And this rotation fundamentally changes the entire geometry of space-time surrounding the black hole in profound and consequential ways. Imagine a black hole slowly rotating, or imagine one spinning at near the speed of light, completing millions of rotations per second. And as it spins, it drags space-time around itself in a phenomenon called frame dragging, where the very fabric of space and time is tormented by the black hole's angular momentum. The 32nd fact is that a rotating black hole is described by the Kerr metric, named after New Zealand physicist Roy Kerr, who discovered it in 1963. And this mathematical description is far more complex than the Schwarzschild metric that describes non-rotating black holes. In the Kerr solution, space-time is twisted and warped in intricate ways that create regions with properties that seem impossible, including a region called the ergosphere, which surrounds the event horizon like an invisible shell where space-time itself is forced to rotate. The 33rd fact tells us something truly extraordinary. If you were to fall into a rotating black hole, you might theoretically pass through the event horizon and emerge into a different part of space-time, possibly even a different universe entirely. And while this remains highly speculative and quantum effects probably prevent such cosmic tunneling, it represents the kind of profound possibility that emerges from Einstein's equations. The 34th fact introduces us to the Penrose process conceived by physicist Roger Penrose in 1969, which suggests that energy could theoretically be extracted from a rotating black hole by dropping objects into its ergosphere and harvesting the energy released as they spiral inward. While no practical method exists to harness this energy, the Penrose process demonstrates that rotating black holes are not merely passive cosmic objects, but rather potential engines of tremendous power. And this realization hints at the profound interconnection between gravity and energy. The 35th fact shifts our perspective to the accretion disk, the swirling ring of material spiraling toward a black hole. And these disks can span millions of kilometers across and reach temperatures of millions of degrees as friction heats the material and gravitational potential energy is converted to heat and radiation. When you look at an image of an accretion disk, you are literally seeing gravity at work, watching matter fall toward doom. And this process represents one of the most efficient energy conversion mechanisms in the universe, more efficient than nuclear fusion in converting matter to energy. The 36th fact reveals that the friction in these accretion disks comes from magnetic fields embedded in the ionized gas, and a discovery made in 1991 by physicists Steve Balbus and John Hawley showed that these magnetic fields become unstable in a way that creates powerful currents and forces that slow down the infalling material. This magnetic reconnection and turbulence causes material to lose angular momentum and spiral inward. And without this magnetic instability, accretion disks would not work the way they do. Meaning that understanding the detailed physics of accretion requires understanding the interplay between gravity, magnetic fields, and plasma dynamics. The 37th fact tells us about jets, which are among the most spectacular phenomena associated with black holes. For some, accreting black holes emit narrow beams of radiation and particles that can extend millions of light years into space at near the speed of light. These jets transport tremendous amounts of energy away from the black hole, and they can alter the structure of entire galaxy clusters, heating the intergalactic medium and preventing new stars from forming across vast cosmic volumes. The 38th fact is that astronomers can observe these jets from billions of light years away because they emit enormous amounts of radiation. And by studying them, we learn about the black hole's spin and the strength of its magnetic fields. The 39th fact reveals something that connects back to the information paradox. If black holes are truly black and unable to emit radiation, then they must actually be perfect absorbers of energy, and this realization led Jacob Bekenstein in 1972 to suggest that black holes must have entropy, a measure of disorder or information content assigned to their surface area. When Stephen Hawking published his discovery of Hawking radiation in 1974, the existence of black hole entropy was confirmed, for entropy and temperature must be related, and a black hole with entropy must also have temperature and must radiate. The 40th fact creates a moment of meditative pause. Here we see that black holes, these seeming monuments to destruction, actually possess thermodynamic properties similar to ordinary objects. They have entropy and temperature, and they obey the laws of thermodynamics just as surely as a cup of tea cooling in a room obeys those same laws. Let us now celebrate what humanity has achieved in detecting and photographing these most elusive cosmic objects, for the story of how we discovered black holes is a testament to human ingenuity, persistence, and the power of collaborative scientific inquiry. The 41st fact takes us back to 1784, when a British clergyman named John Michell made a remarkable calculation based on Newtonian gravity and reasoned that a star with the same density as our Sun, but 500 times its radius, would have an escape velocity exceeding the speed of light. And he correctly noted that such objects would be dark and detectable only through their gravitational effects on nearby visible matter. This insight, made long before Einstein revolutionized our understanding of gravity, shows that the concept of dark, massive, invisible objects pulling on visible matter was already present in the minds of thoughtful scientists, even in the 18th century. The 42nd fact is that when Einstein published his theory of general relativity in 1915, he predicted something remarkable. Light should bend when passing near a massive object, and this prediction was confirmed in 1919 when astronomer Arthur Eddington observed light bending around the Sun during a solar eclipse, providing the first observational confirmation of Einstein's theory. This triumph made Einstein famous worldwide and opened the door to exploring the implications of his theory. And within months of Einstein's publication, Carl Schwarzschild had solved the field equations describing a point mass, laying the mathematical foundation for all future black hole research. The 43rd fact reveals that for decades after Schwarzschild's discovery, black holes remained mathematical curiosities with no observational evidence they actually existed in the real universe, and many physicists were skeptical that such exotic objects could form naturally. It was not until the 1960s that theoretical work by Robert Oppenheimer and others showed that black holes were a generic prediction of general relativity, that they must form whenever a sufficiently massive star collapsed, and this realization inspired astronomers to search for them observationally. The 44th fact tells us about the first black hole discovered, Cygnus X1, identified in 1971 by astronomers Paul Murdin and Louise Webster, located in the constellation Cygnus about 6,000 light-years away. And this object was discovered not by seeing the black hole itself, but by observing the X-rays emitted by material spiraling into it from a companion blue supergiant star. The detection of Cygnus X1 was a watershed moment for astronomy, for it represented the first direct observational evidence that black holes were real, and it opened the floodgates to an era of black hole discovery and research that continues to this day. The 45th fact is that Cygnus X1 contains approximately 14.8 times the mass of our Sun, and its event horizon spans only about 44 kilometers across, and it orbits with its companion star in a gravitational dance that takes about 5.5 days to complete. The 46th fact reveals that by the 1980s and 1990s, astronomers using ground-based and space-based telescopes had identified several dozen black hole candidates, and the evidence supporting their existence accumulated steadily as observations became more precise and more comprehensive. The 47th fact tells us about a revolutionary technology, the Event Horizon Telescope, an international collaboration that combined data from radio telescopes around the world to create a virtual telescope as large as Earth itself. And this incredible instrument was designed specifically to observe the shadows of black holes against the radiation of surrounding material. The 48th fact is that on April 10, 2019, the Event Horizon Telescope collaboration announced the first ever photograph of a black hole, the supermassive black hole at the center of the galaxy M87, about 55 million light-years away, containing approximately 6.5 billion solar masses. And the image showed exactly what Einstein's theory predicted, a glowing orange ring circling a dark shadow. This image had been processed and analyzed from data collected in 2017, and when it was finally revealed, it captivated the world. For humanity had finally seen a black hole, and that image will forever be remembered as a milestone in human understanding. The 49th fact reveals that the success of the M87 image led immediately to an even more ambitious goal: photographing Sagittarius A star, the supermassive black hole at our own galaxy's center, containing 4.1 million solar masses, and the Event Horizon Telescope collaboration achieved this goal and released the image in 2022. The 50th fact creates a profound realization about what these images mean. They represent not just scientific achievement, but a collective human accomplishment. For thousands of scientists and engineers from dozens of countries collaborated to make these observations possible, and the images represent a moment when we collectively witnessed something that Einstein predicted theoretically a century ago. Now we arrive at insights that connect black holes to the largest structures in the universe and reveal their role in shaping the cosmos itself. And these discoveries represent some of the most profound realizations about how the universe works. The 51st fact reveals something astonishing. Most galaxies, perhaps all of them, contain supermassive black holes at their centers. And the mass of the central black hole appears to be directly related to the mass of the surrounding galaxy. This correlation, discovered in the early 2000s through careful observations by astronomers, including Reinhard Genzel and Andrea Ghez, who would later share the Nobel Prize for this work, suggests something fundamental about how galaxies form and evolve. The 52nd fact tells us that this relationship between black hole mass and galaxy mass is not coincidental, but rather reflects a deep physical connection where black holes and galaxies grow together throughout cosmic history. When a black hole at a galaxy's center actively accretes material, it releases tremendous amounts of energy, and this energy heats the surrounding gas and can blow it away, regulating how many new stars can form in the galaxy. The 53 fact explains that this self-regulating feedback mechanism is crucial for understanding galaxy evolution, for it suggests that black holes actually control the growth of their host galaxies by suppressing star formation when they become too active. This realization overturned the previous assumption that black holes were merely passive objects in galaxy centers, revealing instead that they are active participants in cosmic evolution, shaping the structure of galaxies throughout the universe. The 54th fact reveals that in the early universe, about 1 billion years after the Big Bang, black holes were far more active than they are today, producing quasars that shine with the brightness of trillions of stars and often outshining their entire host galaxies. By observing these distant quasars, we are looking back in time to the early universe, and we see that black holes were fueling vigorous star formation and galaxy growth during the cosmic noon era when the universe was most productive. The 55th fact tells us that the population of black holes and the population of stars in galaxies have declined together over cosmic time, suggesting that as the universe has aged, both black hole accretion and star formation have slowed dramatically, and the universe today is far quieter and less violent than it was in its youth. The 56th fact is that this evolution of black holes and galaxies is intimately connected to the structure of the cosmic web itself. The network of filaments and clusters that constitutes the large-scale structure of the universe, and black holes at galaxy centers influence the properties of the gas in galaxy clusters. The 57th fact reveals that when supermassive black holes in galaxy cluster centers become very active, their jets can heat the surrounding intergalactic medium to temperatures of billions of degrees, preventing gas from cooling and collapsing to form new stars. And this process, called active galactic nuclei feedback, shapes the distribution of matter throughout the universe on the largest scales. The 58th fact tells us about something deeply profound. We are not merely observing black holes as external phenomena, but rather recognizing that we ourselves are products of a universe shaped by black holes, for the galaxies that formed the stars, that created the chemical elements in our bodies, were themselves shaped by central black holes. The 59th fact creates a moment of cosmic contemplation. When we study black holes, we are studying the architects of cosmic structure, the engines that powered galaxy formation and stellar birth throughout the universe's history. The 60th fact brings us to a synthesis. Black holes are not isolated curiosities, but rather fundamental components of cosmic evolution. And understanding them means understanding how the universe itself transformed from a smooth, uniform state in the early cosmos to the rich, complex, structured universe we observe today, filled with galaxies, stars, planets, and ultimately with life and consciousness capable of contemplating these cosmic mysteries. As we reach the heart of our cosmic meditation, let us contemplate the great unsolved mysteries that black holes still hold, and the frontiers that await future generations of astronomers and physicists. The 61st fact reveals that the information paradox, despite decades of intense theoretical work by the world's greatest minds, remains fundamentally unresolved. And this unresolved puzzle sits at the intersection of quantum mechanics and general relativity, where our two greatest theories of physics seem to contradict each other. When Stephen Hawking discovered that black holes emit radiation in 1974, he showed that they are not completely black, but this discovery created a profound problem. If a black hole evaporates completely through Hawking radiation, what happens to all the information about the matter that fell into it? Does this information get destroyed? And if so, how can this be compatible with quantum mechanics, which insists that information cannot be destroyed? The 62nd fact tells us that Stephen Hawking himself spent decades wrestling with this paradox, and in 2004, late in his life, he proposed that information might actually be preserved in subtle correlations within the Hawking radiation itself, suggesting that quantum gravity effects we do not yet fully understand might restore information preservation. The 63rd fact is that various theoretical approaches have been proposed to resolve the paradox, and one particularly intriguing possibility is the holographic principle, which suggests that the three-dimensional universe we experience might be encoded as information on a two-dimensional surface at the cosmos's boundary, similar to how a hologram encodes a three-dimensional image on a two-dimensional film. If the holographic principle is correct, it would mean that information falling into a black hole is not destroyed, but rather is encoded on the black hole as event horizon, the same way that three-dimensional information can be encoded on a two-dimensional holographic surface. The 64th fact reveals another speculative but fascinating possibility. The fuzzball proposal developed by physicist Samir Mathur suggests that the black hole event horizon is not a smooth, empty boundary, but rather a quantum structure composed of superposed strings, and this structure would preserve information about everything that fell into the black hole. The 65th fact tells us about the firewall paradox proposed in 2012 by physicists Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully, which suggests that if information is preserved, then the event horizon cannot be as smooth as Einstein's theory predicts, but must be replaced by a seething barrier of radiation called a firewall, though this contradicts the principle of equivalence at the heart of general relativity. These contradictory solutions highlight how profound the mystery is, for each proposed resolution creates new problems, suggesting that our fundamental understanding of gravity and quantum mechanics is incomplete and awaiting revolutionary new insights. The 66th fact is that intermediate black holes remain puzzling, for while stellar black holes and supermassive black holes are well documented, the intermediate range, containing thousands to millions of solar masses, has proven difficult to populate, and astronomers continue searching for these missing objects. Some recent discoveries suggest that intermediate black holes might form through the merger of smaller black holes, or through runaway stellar collisions in dense star clusters, or through the direct collapse of massive clouds in the early universe. But the relative importance of these formation channels remains mysterious. The 67th fact tells us that gravitational wave astronomy, the new window on the universe opened by the 2015 detection of merging black holes, continues to reveal surprises, including black holes that seem too massive or too light for conventional formation theories. The 68th fact reveals that astronomers have discovered black holes of unexpected sizes, including gravitational wave events that suggest black holes with masses that existing theories struggled to explain, hinting that we do not fully understand how black holes form and grow. The 69 fact is that the future of black hole research will likely involve connecting multiple lines of evidence: gravitational waves, electromagnetic radiation, accretion disk dynamics, and theoretical physics into a unified picture. The 70th fact creates a contemplative moment. These unresolved mysteries represent not failures of science, but rather its greatest strength, for they point to frontiers where future discovery awaits, where brilliant minds will wrestle with profound questions, and where the universe will eventually reveal its deepest secrets to those patient and clever enough to listen. Now let us integrate all that we have learned and recognize the profound implications of black holes for understanding the universe's fundamental nature and architecture. The 71st fact reveals that black holes might ultimately provide the bridge between quantum mechanics and general relativity, the two great pillars of modern physics that currently seem incompatible. And perhaps understanding how black holes behave at the quantum level will illuminate the path toward a unified theory of everything. The 72nd fact tells us something remarkable. If we could somehow develop a quantum theory of gravity, it would necessarily explain black holes at the quantum level, resolving the information paradox and answering questions about what happens at the singularity, and this unified understanding might revolutionize our view of reality as profoundly as Einstein did in 1915. The 73rd fact is that black holes might be connected to the structure of space-time itself at the most fundamental level. And some physicists propose that space-time is not fundamental but rather emergent, arising from deeper quantum entanglement structures. And in this view, black holes and their thermodynamic properties would play a central role. The 74th fact reveals that the entropy of a black hole, proportional to its surface area rather than its volume as classical thermodynamics would suggest, hints at this deeper structure and this unexpected relationship between entropy and area discovered by Jacob Bekenstein remains one of the most profound mysteries in theoretical physics. The 75 fact tells us that black holes might be keys to understanding dark matter and dark energy, the mysterious substances that comprise 95% of the universe. For primordial black holes formed in the early universe could constitute some or all of the dark matter we observe, and understanding black hole thermodynamics might illuminate the nature of cosmic acceleration. The 76th fact is that if primordial black holes exist in sufficient abundance, they would have profound implications for cosmology, for they would represent a major component of the universe's matter content, and their detection would rank among the greatest discoveries in physics. The 77th fact reveals that researchers have proposed detecting primordial black holes through their gravitational lensing effects on distant objects and through the gravitational waves they produce. And current and future observatories might discover signatures of these cosmic remnants. The 78th fact tells us about the ultimate fate of black holes. As the universe ages and expands, eventually, given enough time, all black holes will evaporate through Hawking radiation, and the universe will reach a state of maximum entropy where nothing remains but particles dispersed infinitely far apart in an infinitely large cosmos. The 79th fact creates a profound contemplation. We live in a universe that is not eternal, where even the most massive objects eventually fade away. And in this vast temporal expanse, the period when the universe contains stars, planets, galaxies, and life represents merely a brief chapter in cosmic history. The 80th fact brings us to a unified synthesis. Black holes, from the smallest primordial remnants to the most massive galactic engines, represent a thread connecting nearly every major area of modern physics and cosmology, and understanding them means understanding the universe's deepest nature. As we drift toward the conclusion of this journey through the cosmic darkness, let us reflect on what black holes mean, not merely as objects of scientific inquiry, but as expressions of the universe, its profound nature, and our place within it. The 81st fact synthesizes everything we have learned. Black holes are not mere astronomical objects, but rather windows into the fundamental structure of reality, expressions of gravity in its most extreme form, and crucibles where quantum mechanics and general relativity meet and demand reconciliation. The 82nd fact tells us something deeply human. We are made of matter that might have been inside stars and black holes eons ago, and the atoms in our bodies were forged in stellar furnaces and scattered into the cosmos by supernovae, making us literally constructed from stardust. When we contemplate black holes, we contemplate the processes that created the elements that comprise our physical existence, and in this sense, studying black holes is a form of cosmic self-knowledge learning about the universe's machinery that enabled our very existence. The 83 fact reveals that black holes have inspired us not just as scientists, but as artists, philosophers and dreamers, and they occupy a special place in human imagination as the ultimate expression of cosmic power and mystery, the place where normal rules cease to apply and the impossible becomes real. The 84 fact is that throughout history humans have gazed at stars and wondered about the universe, and now we can tell children that some of those stars harbored black holes, invisible cosmic monuments to gravity's power, and we can show them photographs of black hole shadows, images captured by human ingenuity and international cooperation. The 85 fact tells us that the pursuit of understanding black holes represents something essentially human, our drive to comprehend the incomprehensible, to measure the unmeasurable, and to illuminate the darkness of the unknown through reason and observation. The 86 fact reveals that black holes continue to surprise us, for each observation reveals nuances and complexities we had not anticipated, demonstrating that nature is far more subtle and intricate than our theories had predicted. The 87 fact is that future technologies, telescopes more powerful than any currently existing gravitational wave detectors, of unprecedented sensitivity and theoretical frameworks we have not yet imagined, will continue to reveal black hole mysteries, and we invite you to join us on this ongoing exploration of the cosmos. We might eventually image the event horizons of dozens of black holes, map the structure of accretion disks with exquisite detail, and detect primordial black holes from the universe's earliest moments. And if you share this passion for cosmic discovery, we encourage you to subscribe to Beyond the Stars, where every week we explore new dimensions of astronomical wonder and cosmic revelation. The 88 fact creates an emotional crescendo. Through the study of black holes, we encounter the limits of human knowledge and the vastness of what remains unknown. And this encounter should inspire not despair, but rather wonder and humility. And by subscribing to our channel, you become part of a global community dedicated to pushing back the boundaries of cosmic ignorance. The 89 fact tells us that exploring black holes is fundamentally an exploration of ourselves, for it reflects our curiosity, our intelligence, and our stubborn refusal to accept mystery as final. Instead, treating each question as an invitation to probe deeper. And we would be honored to have you join us on this journey by clicking that subscribe button and enabling notifications so you never miss an episode. The 90th fact completes our journey with a unified insight. Black holes are not merely astronomical objects orbiting in space, but rather aspects of the universe's fundamental nature, expressions of how gravity, spacetime, and quantum mechanics interact at the deepest levels, and they represent one of humanity's greatest achievements. The recognition and eventual understanding of phenomena so extreme and so profound that they seemed impossible until reason and observation proved them real. And by subscribing to Beyond the Stars, you support the creation of this contemplative educational content and become part of a movement to bring cosmic wonder into the world. As we now conclude and drift into rest, remember this: the universe contains mysteries that transcend our current understanding, and black holes are among the greatest of these mysteries, inviting us to deeper knowledge and profounder wonder. And we invite you to continue this exploration with us by subscribing to our channel and sharing these episodes with others who also feel the cosmic pull toward understanding. 50 billion years from now, when the last black hole in the universe has evaporated, when the cosmos has reached maximum entropy and final cold darkness, information about that black hole might still encode in subtle patterns and quantum correlations the entire history of everything that ever fell into it. Every star, every planet, every moment of existence compressed into radiation spreading toward infinity. And we hope that the knowledge you've gained from this episode will continue to radiate outward in your own life, inspiring curiosity and wonder in everyone you encounter. In contemplating black holes, we contemplate eternity, and in doing so we recognize that we are part of a cosmos so magnificent, so intricately structured, so profoundly beautiful that words seem inadequate to capture its majesty. And this beauty is even more profound when shared. So please consider subscribing, commenting with your own thoughts about black holes, and sharing this episode with friends and family who might find inspiration in cosmic contemplation. May this journey through the darkness leave you with a sense of peace, with a deepening awareness of the universe's profound mysteries, and with the knowledge that you share this cosmos with phenomena far stranger and more beautiful than any human imagination could fabricate. And may your subscription to Beyond the Stars represent a commitment to ongoing discovery and wonder. The universe whispers its secrets to those willing to listen with open minds and wondering hearts, and black holes are among its most eloquent utterances, speaking across billions of years and billions of light years to tell us stories of gravity, of time, of matter, and of the cosmos's endless invitation to explore, to question, and to understand. And we thank you for listening and warmly invite you to join our community of cosmic explorers. As sleep overtakes you and dreams begin their gentle work, carry with you the knowledge that somewhere in the vast darkness of space, black holes continue their eternal vigil, bending space-time, radiating energy, evolving slowly through cosmic ages, reminding us that the universe is not a static backdrop, but rather a dynamic, evolving, endlessly fascinating realm where mysteries await those brave enough to seek them, and know that by subscribing to Beyond the Stars, you join thousands of others in this ongoing quest for cosmic understanding. And know that future generations will continue this exploration, will ask new questions, will develop new theories, and will ultimately integrate black holes into an even grander understanding of cosmic reality that we cannot yet imagine, just as Einstein could not have imagined the Event Horizon Telescope, and Schwarzschild could not have imagined gravitational wave detection. And we hope that you will be part of this future, contributing your curiosity and wonder to the great collective human endeavor to understand our place in the cosmos. The journey of understanding black holes, like the universe itself, continues without ending each discovery, opening new questions, each answer suggesting new mysteries in an eternal spiral of deepening knowledge that reflects something profound about the nature of consciousness itself, forever reaching toward understanding, forever drawn to the cosmic darkness and determined to make it luminous with the light of human insight. And we hope you will join us again soon as we explore new frontiers of astronomical wonder, right here on Beyond the Stars. Thank you for being with us on this journey, and may the mysteries of the cosmos continue to inspire your dreams.